Katz centrality offers an extension onto eigenvector centrality in which we add a constant term to our iterative formula that essentially gives a default or base amount of centrality to all nodes. That means that all nodes will eventually have non-zero centrality, which was a problem when dealing especially with directed networks in eigenvector centrality. So now we update our equation, which used to look like this for eigenvector centrality. Now we add this extra constant term. And one of the beautiful things about this is that the parameter beta, because we really only just care about the ranking of nodes, not based on the absolute value of their centrality, then the value that we pick here for beta ultimately doesn't matter. What you're going to see here is that this beta enters as just this scalar multiple, and so it doesn't really matter what that value is. So just like eigenvector, if we think about this as an iterative process where we're passing centrality through the network along the edges, which is encoded in the adjacency matrix A, that we reach a steady state when this vector is no longer changing. So when at the next time step you have the same value that you had coming in, then you've reached that steady state. And then the other parameter that we're going to have in Katz centrality is this alpha term. And so that alpha is really the balance between how much we balance the eigenvector portion and how much we value the constant piece. And so keeping in mind the idea that if alpha is equal to 0, that essentially you just have constant centrality or equal centrality for everyone. And so then as alpha increases, you lean a little bit more towards the eigenvector definition as alpha gets bigger. So if we set these things to be equal, then we just let that essentially gives us the fact that x is equal to alpha ax plus beta times the ones vector. And so if we rearrange this allows us to solve for x by combining those terms, and that gives us this inverse here. And so whenever you take an inverse, it's important to be careful about when that exists. And so we know that alpha is equal to 0. That corresponds to this constant centrality. That is, in that case, then you just have the identity matrix, which is invertible. And so that's no problem. So then the question is, for what values of alpha continue to be invertible? This matrix I minus alpha A. When do those continue to be invertible? And then what's the first point that makes of alpha that makes this value, this matrix here, singular? So we're curious about when the matrix I minus alpha A becomes singular. And so one of the ways to determine whether it's singular or not is to look at the determinant of this. So the determinant of a matrix, if that's equal to 0, that means that matrix is singular and it's no longer invertible. So we're curious to know what values of alpha make I minus alpha A singular. And so that's essentially what I've put down here. If we go ahead and divide by alpha, that just allows us to rearrange this equation. In fact, we're dividing by minus alpha. And that doesn't change the determinant, and it also doesn't change mainly because you can just pull that minus alpha out. So if I pull minus alpha out here, I get determinant of A minus 1 over alpha times I, and that's equal to 0. And so because this is equal to 0 on the right-hand side, I can just get rid of that minus alpha by dividing by minus alpha on both sides. So now I'm looking at this new expression, and that's essentially what I have here. And so the insight that we're going to use is the fact that if we look at the eigenvalue eigenvector equation, we're going to have A, let's call this W, is equal to lambda times W, where lambda is the eigenvalue, W is the eigenvector. So if I bring those sides together, I can form this A minus lambda I times W is equal to 0. And so when the determinant here is equal to 0, that implies that there is a vector that makes that when I multiply by this vector, I can get 0. So there exists this. If this quantity is invertible, then there is no w except for a vector that's all zeros that will actually make this 0. So it's the fact that this is singular that enables me to come up with a w vector that essentially annihilates that matrix. And so what we're seeing now is we're seeing this on the left-hand side, which came from our interest in figuring out what values of alpha make this matrix singular. And we look at this, which comes from the definition of the eigenvalue eigenvector equation. And what we see is that when alpha is defined such that 1 over alpha is equal to lambda, we will necessarily make this matrix singular, because that's the way that the lambda, the eigenvalue and eigenvector are defined. So they're defined to satisfy this equation. That means that lambda is a value that makes this matrix singular, and w is the vector that annihilates it. And so since we're using the same matrix A, we can pick alpha to be, so the other way to write this is that we say alpha is equal to 1 over lambda. When that's the case, then this matrix A minus 1 over alpha times I is singular, which then means that this matrix up here, I minus alpha A, is also singular. Okay, so we know that when alpha is picked to be the reciprocal of any of the eigenvalues, that we get a singular matrix here, which is something we want to avoid. We know that when alpha is equal to 0, it's a valid quantity, and so we can go ahead and use that, and we can take the inverse, so that's valid. And now what we're going to do is we're just going to keep increasing alpha until we get to the point where we hit that first eigenvalue, or 1 over that first eigenvalue. And so which one comes first? If lambda 1 is the biggest, then 1 over lambda 1 is the smallest value. And so that becomes the first one that we hit as we move away from 0. So at this point, picking alpha is equal to 1 over lambda 1, that's the first point at which value of alpha, that makes this quantity singular. And so this is then our interval of alpha values that yield reasonable and interpretable, meaningful centrality values for Katz centrality. And so that's our argument to say why alpha has to be within this interval. Pagerank is another extension of both eigenvector and Katz centrality that allows us to kind of normalize centrality based on out degree. And so in the labs, you're gonna look through and justify why alpha is on this interval from 0, in this case, up to 1. And that is largely driven by the fact that we're going to be looking at comparing this exact same derivation with our Katz centrality approach. The only difference here is now, instead of looking at just the matrix A here, now we have the matrix A D inverse, where that D inverse does this normalization. So in what you do in the lab, you're going to specifically take a look at and apply that Katz proof that we just went through to this particular case, where now we've changed this matrix here to be AD inverse instead.